In the last session, you've seen a class hierarchy of overall 3 classes. A real program, of course, would contain not 3, but dozens or hundreds or thousands of classes. So there's a question how to organize them. In this session, you'll learn about packages that can contain classes, as well as how to make classes accessible with imports. You'll find out about the standard Scala library that contains a lot of predefined classes already, and how these classes are organized in a hierarchy.
So generally in Scala as well as in Java, classes and objects are organized in packages. You can place your class or object inside a package simply by adding a package clause like package procfun.examples at the beginning of your source file. And that would put then every class or object you define later on in that package that you have defined here. And once you've done that, then you can refer to the original object or class by its so-called fully qualified name. So the fully qualified name is the name of the package and then a dot and then the name of the object or the class. So for hello, it would be procfun.examples.hello. And that fully qualified name you can use to refer to hello from your program, or also on the command line when you say want to run the hello program, you would write Scala and then procfun examples hello. So let's demonstrate that using the worksheet. What I've done here is I've taken the class rational from the last session, which was in a worksheet, and I've put this as a standalone class in package week 3 over here. So now what I want to do is refer to rationals from another worksheet, call it Scratch. So what we could do is write new week 3 dot rational of 1 and 2. And then the worksheet would answer that it's defined a instance of type week 3 dot rational and the value is 1/2. So if it becomes too tedious to write week 3 dot rational every time you want to refer to a rational, you could also import the rational type from the week 3 package. The way you do that is with an import clause. You write import week 3 dot rational. Once you've done that, you can refer to rational without the prefix because you have imported it previously. Imports come in several forms. This is the most simple one where you import a single named thing. There's also another form of import where you import everything in a given package. So the form import week 3 dot underscore would import everything that is defined in package week 3. It's more general, it's more convenient, but sometimes it's less legible because sometimes you really want to have a more precise control over where your names come from. There's also a third form of import, which you see here in the second line, where you can import several names from the same package. So the form import week 3 and then rational, hello in braces would import both rational and hello from the week 3 package. The first two forms here are called named imports, and the last form is called a wildcard import. And another thing to say is that we've seen we can import from packages, but you could in fact import from any object, any expressions that gives you an object, and you would simply import all the members of that object. Some entities are imported automatically in any Scala program. These are all members of package Scala, all members of package Java lang, and all members of the singleton object scala.predef. So if you wondered previously, for instance, where did the require or the assert function come from? Well, the answer was they were defined in the object scala.predef, that's an object inside the Scala package, and the automatic import of all members of the predef object made that you could use these names without a further qualification. The same holds for the types int and boolean that you've used before. So these are actually defined in the Scala package, and their fully qualified names are scala.int and scala.boolean, whereas the name object that we've been using, that actually comes from the Java universe, in which essentially the Scala universe is embedded. Object is spelled out java.lang.object. the root object of all Java objects, and we have imported that automatically because besides Scala also all objects in Java lang are automatically imported. So by now you probably would like to find out more about what classes are there in the Scala library, what can you do with them, what methods do they export. You can do all that using a set of web pages that have been generated by a tool called Scala Doc, and you can get at that by either googling for Scala Doc or going to this page here, which gives you the root package of the Scala library. And here you can see on the left hand side the set of classes. You can, by displaying all packages, you get the set of packages in the Scala library. If you go through to the package Scala, then, and I look at a class, let's say the predef object that we've seen here, then you see here an explanation of what's in the predef object. If we then want to find a method, let's say assert in there, then you see here is the definition of the assert methods that are offered by the predef object. You see here each assert comes in two versions, one with an error message, one without. So that's why I told you the error message was optional. And like that, you can explore what's out there in the Scala libraries. Now, if you have browsed a little bit the Scala doc, then you probably will have come across a set of pages that describe traits, and you might ask, well, what is a trait? Well, in Java, as well as in Scala, a class can only have one superclass. We say for this scheme, it's a single inheritance language. Single inheritance. And that's actually very constraining because quite often a type would have naturally several supertypes, or you would want to inherit behavior from several super entities that all contribute to the final code of the class. To do that, you can use a concept called traits. A trait is essentially declared like an abstract class. You just use trait instead of the keyword abstract class here. So here we would have, for instance, a trait of planar objects where the objects would have a height and a width unspecified, so those defs don't come with an implementation. And then you would have a surface that would be height times width as a default implementation. So that would be a concrete method, and those two would be methods which lack an implementation and so are called abstract. So the idea of traits is then that classes, objects, and other traits, they can inherit from at most one class, but they can inherit from arbitrarily many traits. The way you do that, you see here. So here you would have a class square that extends, let's say, a shape superclass, and then it adds also two traits. One is called planar and one is called movable. You combine the superclass and all the traits you want to inherit with width here. So width is a combination that adds another trait to some set of classes or traits that you inherit already. In that sense, even though the syntax is different, traits resemble interfaces in Java, because in Java as well you can inherit from one class but multiple interfaces. However, traits in Scala are actually much more powerful than interfaces in Java, because traits can contain fields and concrete methods, whereas interfaces can contain only abstract methods. We've seen on the last slide that the trait planner has had one method surface, which already gave a default implementation of the surface property here. That implementation can be overridden in subclasses, as always, but if subclasses do not give an implementation, then this one here would be chosen. So there's only one thing you can do with classes but not with traits, and that is that classes can have value parameters, like the numerator and denominator of class rational, whereas traits cannot. So traits never have parameters. So now let's have a look at the outline of Scala's class hierarchy. So here you see the fundamental Scala classes and the relationship between them. The arrow here means that the class at the root of the arrow is a subclass of the class to which the arrow points. So you see that the classes are organized in a hierarchy. At the top of the hierarchy, you have a class called Scala.any. That's a superclass of every other class. And then you have essentially two sub trees of classes. They are rooted in anyval and anyref. So anyval is the base class of all so-called value classes, and those are essentially the primitive types that you see from Java. So you have int and long and float and double and boolean, and those types would all be subtypes of Scala.anyval. All the other classes are subtypes of Scala.anyref. Anyref itself is just an alias, a different name for Java-lang object, the root class of all Java classes. And here you see classes like the string class of Java, but you also see Scala classes such as iterable and sequence and list. We will get to know them later on. All those classes happen to implement another trait called Scala.ScalaObject in addition to the anyref base class. And then on the bottom of the slide you see two types that are subtypes of many other types. They are called Scala.nothing and Scala.null, and we'll get to them in the following slides. I should say there's one other twist here in this diagram. You see the relationships between the numeric types. They are actually written with dotted arrows, not hard arrows. And that means that the numeric types, they're not strictly in a subtype relationship with each other, but in a conversion relationship. So you can automatically convert a type such as long to a float, but it's not really a subtype. Why is it not a subtype? Well, a subtype really means that the conversion is the identity, so that you don't need to rearrange the bits in order to go from one type to the other. Whereas here, definitely, if you go from a long to a float, you do need to change the representation of that type. And what's more, in this case here, the conversion is not loss-free. You might actually lose some precision going from a long to a float. Looking again at the top types in the hierarchy, we have three of them: any, anyref, and anyval. Any is the base type of all types, and it's also the type that defines certain universal methods. We have already used equality equals equals and its opposite not equals. Those are actually methods that are conceptually defined in this type any. And those methods actually map to their Java equivalents, which would be written equals. That's the root method of Java. So equals equals is essentially just a forwarder that calls the Java equals methods unless it's overridden by the user code. And also in class any you would find the method toString that you've already seen that converts an object to a toString. And finally you'll have a universal hashcode method that produces a hash code from an object. The two subtypes of type any are then anyref, which is the base type of all so-called reference types, and that's an alias of Java-lang objects, and anyval, which is the base type of all value types, which for the time being are just the primitive types that Scala inherits from Java. So what about those two types at the bottom, nothing and null? Nothing is at the very bottom of all Scala types. It's a subtype of every other type. And there's no value that has type nothing. So you might ask, well, why is that useful? How is a type that has no value useful? Well, there are actually two uses, and the two uses, it turns out they're connected. The first is to signal abnormal termination. Sometimes a function would not return, but for instance would throw an exception or abort the program. And in that case you might ask, well, what would the return type of that function be? And the answer, in fact, is the best possible, the most precise possible type is nothing. It doesn't return anything. It will terminate abnormally. And the second usage that we are going to see shortly is as an element type of empty collections. So if you have, let's say, a set that contains no elements, you could say it's a set of nothing, something like that. We will see that in a second later on. So speaking of abnormal termination, the usual way that is brought about in both Java and Scala is using an exception. And in fact, here the syntax for both Scala and Java is exactly the same. You have a throw expression where you write throw, and then comes some exception value. And that throw expression would then abort the evaluation of the program with the given exception. Let's do that in an example. Let's say we have a function f_def error, and it takes a message of type string, and it should give us a throw new. Error is an exception with the given message. So calling error would immediately abort the program. So what we see here is that the computed type for error it's a method that takes a string as an argument, and it will return nothing. So the Scala type checker was able to figure out that this expression will not terminate normally, and therefore its result type is nothing. Indeed, if we call error now with some exception value, then what you would get is not normal termination, but you would get an exception trace that says, well, and the exception java_lang error was thrown, and that was the message that came with it. The other bottom type we have in the diagram is Scala.null. Turns out that null is a subtype of all the classes that are themselves reference types, and it's also the type of the null value. Null is written in Scala as in Java. It is a value of every reference type here. So when somebody expects, let's say, a string, you could also pass it null. So the type of the null value then is the null type, which is written in the same way, just with a capital N. And that type is a subtype of every class that inherits from object. On the other hand, it's incompatible with subtypes of any val. So let's try that out here. So we could write first val x equals null. And here the worksheet would answer that the value of x is null and the type of x is null with a capital null. We can also then assign x to another value of, let's say, type string. And you see that also works. So the value x with the type null, that one actually conforms to string, so you can initialize the value y with the value x. On the other hand, what you cannot do is define a value of type int, say, and initialize that one to null. There you will get an error which says that there's a type mismatch. The compiler found null, the null value of the null type, and it required an int. And then there comes a long string that certain implicit conversions are not applicable, which you can ignore. So you've seen that null is a subtype only of the reference types, not of the value types. Let's do an exercise. Let's say I have the following expression: if true 1, else false. What should the type of that expression be, in your opinion? Possible answers would be int, or maybe boolean, or maybe any val, or object, or any. Well, to solve this question, the easiest thing would be to just enter this expression into the worksheet and see what it says, right? So if true 1, else false. What do we get? We get any val. Why do we get any val? Well, let's look at the two branches of the if. The first one is 1, has definitely type int. The second is false, and that has definitely type boolean. but then those two types don't match at this level. So what do we do? Let us look back at the hierarchy here. So we see that we have int here and we have boolean here, but both of these values are also values of the supertype. So that would be either anyval or any. And in this case, anyval is better. It conveys more information than any. So the type checker actually picked the type that matched both of these values, anyval in that case, and that was as specific as possible. So that's why the type checker answered with anyval.